we have a rectangular waveguide, and the parameters which are given, we have an A, which is 2.3 centimeters, we have a B, which is 1.0 centimeters, and then the medium inside this waveguide, it is not air, but it is some dielectric, which is described by relative permittivity, which is 2.25, and then we have a relative permeability, which is equal to 1. Now, what we are asking here, let's find H, Fc, lambda c. So for Tm11, find H, find the cutoff frequency, and the cutoff wavelength. So let's find these parameters. First of all, the H squared, this is equal to m pi over A squared plus m pi over B all squared. Okay, so the A and the B, we know them. It's not that difficult. And then we have also the expression for the cutoff frequency. So the cutoff frequency as a function of m and n, this is equal to 1 over 2 permeability times permittivity times the square root of m over a squared plus n over b all squared. Then we can also write down the wavelength, cutoff wavelength, which is equal to, we can write this one as 2 divided by, wait a second, 2 divided by m over a squared plus m over b all squared, or simply 2 pi over h. Okay. So, given these equations, let's try to determine the relevant quantities that we are looking for. And first of all, if we insert here for h, Tm11, this will be equal to, let's use meters. So m is 1, this is pi over 2.3 times 10 to the power minus 2 all squared plus pi over 1 times 10 to the power minus 2. This is all squared, and this is equal to, we have to take the square root of this term for sure. And what is this? Approximately, let's see. This is 3 divided by 2. This is approximately 1, but it's larger than 1. Divided 10 to the power minus 2. This means that this is 10 to the power plus 2 squared. This is 10 to the power 4. Okay, approximately the first term. The other term, this is 3 times 10 to the power plus 2. This is 4. This is 9. Okay, so apparently we're having something like 10 to the power 4 times 10, because we factor this together. So we're going to get something which is square root of 10, because we have also the square root of 2, times 10 to the power 2. Square root of 10 is around 3. So we're going to get something, an h, which is approximately to 300. If you are in an exam, you get no points from our class if you don't give at least the order of magnitude. So if this is the order of magnitude, we also care about the approximately, we should get something like this. The unit, it is meter inverse, because the A's and the B's, we converted them into meters. Now, the exact solution here is 342.6. 3.2 times 6 meter inverse, okay? So we found the, what is this? The H. And then we have the cutoff frequency, and the cutoff frequency, this is equal to, so we can write here the cutoff frequency here. It can be written as H, they are divided by 2 pi square root of permeability times permittivity. So, and then this is equal, H, we have this one, is 342.6 divided by 2 pi times, now this is 1 over the mu times permittivity, and this is equal to 1 over mu relative times mu 0, epsilon relative, epsilon 0, okay, and this is equal to mu r is 1, so this is 1 over the square root of ER, mu 0, epsilon 0, and 1 over mu 0, epsilon 0, this is the speed of light, okay, this is c, divided by the square root of ER. So this term that we see here, we can write this one, so this is the h, then this is the speed of light because it's hidden in here. Here we get 3 times 10 to the power 8 divided by the square root of 2.25, okay? And the magnitude here, we're talking about 2 pi, this pi can cancel this 3, we have square root of 2, this is 1.4, so actually we can cancel the 3, 1 over pi. So approximately I can say that the student in the class could rightfully say that this is going to be equal, this cutoff frequency is 1 over pi to some degree, 10 to the power 2, 10 to the power 8, we're talking about 10 to the power 10 hertz, which is in the order of around 10 gigahertz, okay? But the exact number, if you substitute the numbers using a calculator, we get 10.9 gigahertz. 10.9 gigahertz, which means that this is the cutoff frequency. So any for the mode 111. Now this was just rough calculations, so we can take this, we can erase this one because the numbers we entered them here above, and then we added the cutoff wavelength here for the mode 111. It's going to be equal to 2 pi divided by h. This is 2 pi divided by 342.6, 342.6 times 1 over meters. This is the unit of this one. So here we have 2 pi divided by 342.6. The unit is meters because 1 meter inverse, then we get the meters, and this is equal to 1.83 centimeters. Okay, so this is the waveguide. So it looks like the A is 2.3 centimeters. Okay, so let's try to look at this one this way. So this is 1, this is 2.3, and the cutoff wavelength, they are traditionally, this can be A over 2. Okay, so this might be expected to be somewhat related to A over 2. So this is just approximately, okay, because we want to get a feeling of what should be the order of the magnitude of the important quantities. So this A over 2, this is equal to 2.3 divided by 2, we get 1.15, 1.15. But this is the case if the wave was, if this waveguide was air. This is not air, we have a medium which is slightly, well, a lot different. It's a dielectric, which is different from vacuum. Now, so these are important parameters for this specific wave, and then what we can ask is also, now given these, we can also determine what are the inverse Tm or inverse Te. Not inverse, what is the impedance? Inverse, I got confused with intrinsic impedance. So, yeah. And then we can assume, let's assume for a moment, given frequency, which is equal to 1.15 times the cutoff frequency. Okay, so let's assume that we are given the cutoff frequency, we found it, it's 10.9 gigahertz, and let's assume a frequency which is 15% higher than this, and then if we are given this one, we will be asked to find beta mn, find z, find lambda. Now we need to find all of these quantities. But the moment we are given this frequency, it is important for us to immediately figure out what is this term. 1 minus cutoff frequency over the exact frequency square root. Öszmir, the GM direct, the coefficient and oriented. So I call this one Lorentz vector, okay, because it's something very, we're used a lot to it. And we draw this should be the term. This is equal to 0.49. 0.49, okay. And so we're going to use this one in all the calculations that follow. So first of all, we have ZTM for the mode 1, 1. As we remember, we said that the impedance, it drops for the TM modes in a waveguide. So this is going to be equal to the intrinsic impedance times the square root. So in principle, this is intrinsic impedance times 0.49, okay? Because we calculated that there. And this will be equal to, this is 377 divided by the square root of 2.25 times 0.49. So this intrinsic impedance is going to be equal to 124 ohm. 124 ohm. It has dropped. The beta then, beta is equal to, or 1, 1 for transverse magnetic mode. This is equal, this, wait a second, this is also equal to beta times the square root, and the beta itself, it is, wait a second. So we should not forget that beta itself, it is omega times permeability times permittivity. If we substitute all of these relevant parameters, we can put here omega itself is 2 pi times the frequency. 2 pi times the frequency, we have 2 pi times 12.54 times 10 to the power 9. This is the gigahertz, this is the omega, okay? Then we divide by the speed of light, which is 3 times 10 to the power 8, because omega divided by the c, but we have by the speed of light. Then we have 2.25, so we have also this term, times, now we come to this square root, okay? So this is omega times this times the square root, which is here. So then this times 49. So the beta for this specific mode, this is equal to 195. And this is radian per meter. This is the phase, the constant, radian per meter. Okay. And then the final parameter that we can determine is to find the lambda, which is going to be 2 pi over, and this is lambda mn, 2 pi over beta, and this is equal to 2 pi divided by 195. 195. This is equal to 3.23 centimeters. Okay. Do you have any question? Okay, if no question, we can give another break.